right, so we're in chapter 2 now, and in chapter 2, we are going to be focusing exclusively on first order equations, and we're going to be looking at several different things. Most of this chapter is going to be dedicated to techniques for solving first order equations. But this very first section, 2.1, we're actually not going to look at solutions. In fact, the title of this section is Solution Curves Without a Solution. So before we get into this section, I want to mention something about differential equations and a course like this one. The majority of what we're looking at in this course is solution techniques. How do you take a particular differential equation and find a solution for it? And we cover a wide variety of different solution techniques for all sorts of different kinds of ODEs that we can come across. But it can be misleading. By the time you get to the end of this class, it may mislead you into thinking that any ODE that you come across can be solved using the methods that we talk about, or at least most of them. And in reality, it turns out that that's not really the case. In fact, it's actually somewhat uncommon to be able to find an explicit kind of tidy little solution for any given ODE that you come across. And for that reason, there's a necessity for tools that can sort of suss out more information about a differential equation if we are unable to find a solution. So basically what we're looking at here in section 2.1 is if we are given a differential equation, a first order differential equation, what information can we get from that differential equation without necessarily getting a full solution for it? And it turns out there's a good amount of information you can pull out of a differential equation depending on what type you're looking at without ever solving it. That's what we're getting at here. So again, we're focusing on first order ODEs in this section. And what I want to start with is this. So this is what a general first order DE in normal form would look like. dy dx equals some function of your independent variable x and your dependent variable y. Now, looking at a first order equation in normal form and thinking about it in terms of what we know a derivative to represent, this gives us some information about the solution curve, or about a solution curve. What we have here is dy dx equals a function of xy. X and y are the coordinates of a point in the plane, and dy dx represents a slope of a tangent line to our solution curve at that given point. So for that reason, because dy dx is equal to this function of x and y, we refer to this function in this specific case of a differential equation as a slope function. And it's only called a slope function in the case of a first order equation like this, where you've put this in normal form. But we call it a slope function because if I plug in different values for x and y here, the output of this is going to correspond to a slope here, specifically a slope of a tangent line to a particular curve. So this graphic down here kind of illustrates that. Again, suppose I haven't been able to find a solution to this DE up here, but I just want to see what kind of information I can pull out of that differential equation. Let's suppose I plug in, I have some explicit function that I'm working with here, and I plug in a 2 for x and a 3 for y, and out comes some number. I know that that output represents the slope of a tangent line at that point to a solution curve that contains that point. Okay, so that can be useful information. Now, what if we didn't have a solution to work with, but we wanted to determine kind of an idea as to what a solution curve might look like? One thing that you could do is pick a whole lot of different values for your x's and y's here, plug a bunch of those in, and get a whole bunch of different slopes to work with. Then if we were to graph all of those slopes in the plane, it might give us some indication as to what a solution curve could look like. So a little bit of terminology to get us to that point. This little line segment that's drawn right here, representing that a piece of that tangent line to that point, or to the curve at that point, we call that a lineal element. Okay, it's a lineal element representing a piece of a tangent line. And if we graph a whole bunch of lineal elements for a particular differential equation in the plane, we get what's called a slope field, or it's also very commonly called a direction field. Okay, now I'd like to do an example here where we create a slope field, and you'll notice I've already created the slope field by running it through software to do this. But I want to show you what the process would look like if you were trying to do this by hand. So we have a differential equation here, dy dx equals 1/2 xy. Notice that it's in normal form. That means that this function here, the 1/2 xy, is my slope function. What I can do is pick different values of x and y, plug them into this, and those outputs are gonna represent slopes of all of these lineal elements. So I created a table here, and I selected some points to plug in. Notice all of these points have a y coordinate of 1, which is going to correspond to the lineal elements along this horizontal line here, y equals 1. Notice this table will only help me produce these lineal elements. I would need to create a much larger table to produce all the rest of these. But let's just go ahead and fill this table out. So I'm plugging in -3 for x, 1 for y up here. That's 1/2 times -3 times 1. That would be -3/2 there. And then 1/2 times -2 times 1, that would equal -1. And then I'll just go ahead and do all the rest of this. So this will be -1/2. This will be 0. We'll get a 1/2 here, a 1, and a 3/2. Okay, so what we see here for these points where I have a negative x value and my y coordinate here is 1, I'm seeing all negative slopes. So my lineal elements should all be decreasing for these values, but the slopes are getting shallower and shallower. They're kind of approaching 0 as we get towards here. And I'm seeing that happen in the lineal elements corresponding to these points. So here's the one that should have a slope of -3/2. Here's one with a slope of -1. Here's one with a slope of -1/2. Notice once I get to the point 0, 1, my slope becomes 0. That's where I get this horizontal lineal element. And then once we move into these points, the slope becomes positive and gradually gets steeper as we move more towards the right. I'm seeing that exact same thing happen here. Okay, so I didn't do this one by hand. For the homework, you will be asked to do them by hand, and it can be a little bit tricky getting these slopes correct. I recommend doing it with graph paper so you can kind of use the grid to your advantage there. But this is what a slope field for this particular differential equation could look like. One comment on slope fields: all of the values that I used here, and in fact all of the points that I put lineal elements on in this entire slope field, are integer valued. Notice I have a lineal element here at 1, 1, and 1, 2, and 2, 2, and so on and so forth. You can absolutely find lineal elements for points that aren't all integer valued, and if you did that, you would probably get a better looking graph. You would get more lineal elements in there, and you get a better sense of what's going on. The trade-off is that it creates a lot more work for you. So generally, slope fields in practice are not done by hand anyways. We use software to generate these things. And for me, I do want you to know how to create one by hand, but it's more important that you understand how to interpret these things. So let's move on to this next page here. So what is the point of a slope field? Well, the idea behind a slope field is that it gives us an idea as to what a solution curve to our differential equation might look like. So shown here in these different colors are a bunch of possible solution curves to the DE in our previous example. This is the same slope field from that example with a little bit more shown. And I superimposed on this slope field some graphs that I actually know are solution curves for that DE. And look at how they interact with these lineal elements. So for example, each slope or each solution curve very clearly has a horizontal tangent on the y-axis. You can see in all 6 of these that I've graphed on here that they definitely do have either a local maximum or a local minimum where you would expect to see that horizontal tangent. And then as we start creating a curve for this, let's follow this green curve, for example. If I started here at the point 0, 1 and started trying to sketch an approximate slope curve, I could see from all of these lineal elements that surround this right side of the graph that we should be increasing. And so I'm gonna sketch that curve so that it's increasing and kind of following the direction of all of these lineal elements. We're going to do one by hand here in a moment, but one thing I do want to point out is that it's tempting, if you're using a slope field like this one to approximate a solution curve, to try to make your solution curve touch too many of these lineal elements. Notice this green curve, the only lineal element that it's actually tangent to is this horizontal one right here. The other lineal elements it might get close to, but doesn't necessarily hit them. And the reason for that is because these solution curves don't necessarily pass through a bunch of integer valued points where we chose to graph these lineal elements. So you kind of want to resist the temptation to make this thing touch too many of these lineal elements. You just kind of want to follow the general direction. Okay, so to illustrate that with an example, here's a different DE than the one that we saw in the previous example. In fact, this one is an IVP. We have an initial condition here as well. The function or the equation is dy dx equals x over y, and the initial condition is y of 0 equals 1. Now the point of that, the point of being given this initial condition is to provide us with an actual point that will be on our solution curve. This corresponds to the point 0, 1, which would be right here. Okay, so the solution to this IVP, at the very least, we know will have this point on it. Then the next thing I want to do is sketch a curve that passes through this point and sort of follows the direction of these lineal elements. So I can see, if I focus on the part of the graph that's going to be to the right of this point, it looks like all of my lineal elements are increasing, and it also looks that it looks as though it looks like if I move further to the right, they are getting steeper. On any horizontal line passing through here, they appear to be getting steeper. Not only that, it also kind of looks like, if I look at the line y equals x right here, it looks like these lineal elements are aligned. It looks like they all are on the same diagonal line here. To me, that makes me kind of think of this almost like a slant asymptote. So I'm going to kind of use that as a guide, and I'm going to put my curve this way and have it kind of do that. So I'm expecting my curve to sort of approach that as an asymptote. Now looking at the slopes of the lineal elements to the left of my y-axis, they appear to have some symmetry with the ones on the right. They look like a mirror image of these guys. They all have negative slope, but they look like a mirror image. So I'm expecting my graph to have that same kind of symmetry. It would make sense for it to sort of approach this other asymptote going that direction. Now that's not going to be a perfect solution curve by any means. I did it by hand. But using that initial condition and my slopes as a guide, I feel pretty good about that solution curve. Okay? All right. So that's a little bit on slope fields. Now in your book, it takes section 2.1 and breaks it up into 2 little subsections. So slope fields or direction fields, it calls that section 2.1.1. And then this next section, which is about these things we call autonomous equations, it calls that 2.1.2. I'm not using that numbering for my notes here. I'm just calling everything section 2.1, but that should give you an idea of where we are. So as was the case at the beginning of this section, we are focusing on first order equations, and we do like to represent them in normal form, like we did here. Now, an autonomous equation we're going to typically represent them in normal form, or at least put them in normal form if they don't start out that way. But an autonomous equation is a differential equation that does not have any dependence on the independent variable of our solution. So for example here, the dy dx indicates that y is a function of x, but in this differential equation, the independent variable x is not showing up anywhere. I'm not seeing any x's in the actual dE itself. I'm only seeing y's showing up. That's what makes a differential equation autonomous. A differential equation doesn't have to be first order to be autonomous. There's autonomous second, third, nth order differential equations. And in fact, we can even talk about autonomous systems of differential equations. But in this chapter, we're only going to focus on the first order type. So this is what an autonomous differential equation would look like in normal form. dy dx equals some function of only y, not x and y. To give you some explicit examples, this is an autonomous equation. Dy dx equals cosine of y minus y squared, because y is the only variable showing up. This is an equation that is not autonomous. Dy dx equals x squared y cubed. The x makes an appearance here. We do actually refer to these types as non-autonomous. Okay? Now, autonomous equations show up with great regularity in applications. In fact, if you were to go back into the last section that we covered, section 1.3, and look at all those applications that we talked about, I believe every single one of them is an autonomous equation. The independent variable in all of those examples was time, but the variable t doesn't really make an appearance in any of those differential equations, unless I'm forgetting one. I don't think it does, though. There's a good reason for that. This will make a little bit more sense at the end of this section when we talk about this translation property that these equations have. But essentially what that means is that the differential equation itself does not depend on time. The solution to that equation will, but the dE does not. And for that reason, it's very common to refer to these types of differential equations, specifically when the independent variable represents time, as time invariant equations. I don't remember if this term actually shows up in your book or not, but this is a common term that's used with these types of equations. Okay? Now, when we are given an autonomous equation, we're going to talk about some tools that we use to analyze these things to give us a sense of what a solution curve to it might look like. We've already talked about using slope fields, and you can make a slope field for an autonomous equation as well, but you can do even more than that. Okay, so the first thing I want to look at is, did I write? I don't know if I actually wrote this term down. Okay, so before I jump into that, I'm going to start using a term here that I don't think I defined anywhere unless I'm missing it. In an autonomous differential equation, this function right here, that f of y, we call that the slope function. Okay, I don't want to go any further until I talk about that for a second. Oh, no, I'm sorry. We did talk about that over here. Okay, yeah. I'm blanking for some reason. So in this case, I want to look specifically at this slope function. And because it's a function of only one variable, I can find zeros for a function of one variable typically without much trouble, unless it's a complicated function and, algebraically that might be difficult to do. But if we have an autonomous equation and I take that slope function out of there and find the zeros of that slope function, those zeros play a significant role in the analysis that we do with autonomous equations. We call those zeros critical points. And notice something here. If I were to solve the function f of y equals 0 and find the zeros for that function, what I'm finding are values of y, right? So let's suppose that c, the number c, is a critical point of an autonomous differential equation. It's a zero of this function. Then specifically we're saying that y is equal to c. If I think of that as a function though, y equals c, that's a constant function. Okay, so critical points lead us to constant functions that end up being solutions to this differential equation. Now think about why that would be the case. If I have if y equals c and I have a constant on this, or if I have a constant that I can plug into this function and have it become 0, then that leads to dy dx equals 0. And we know that if the derivative of a function is equal to 0, then that original function was a constant function. So that y equals c is going to be a constant function or a constant solution to this differential equation, and those we call equilibrium solutions. Okay. Now, we use those equilibrium solutions to break up the y-axis on a graph when we're looking at solution curves to these differential equations. We use it to break it up into subintervals, and on each one of those independent subintervals, our differential equation will either be entirely positive or entirely negative. We'll illustrate that with this next example here. Analyzing the behavior of a solution curve in those terms, increasing or decreasing, positive slope or negative slope within those subintervals, we do that with something called a phase portrait. So I'm gonna do an example where we do exactly that. Here what we want to do is determine a phase portrait for this autonomous differential equation, and you notice it's autonomous because there's only y's showing up here. dy dx equals y squared minus 4y plus 3. And then what we're going to do is use our phase portrait to create regions in the xy plane on which we can analyze the behavior of a solution curve passing through some point in that region. I'm going to call it x naught, y naught. So here's what that looks like. Okay, first thing we want to do are determine the critical points of this equation here, giving us equilibrium solutions. So I take y squared minus 4y plus 3 because that's the slope function in this dE, and I set it equal to 0. Y squared minus 4y plus 3 equals 0. This factors, I get y minus 3, y minus 1 equals 0, giving me the following solutions: y is equal to 1 or 3. Okay? So y equals 1 and y equals 3. Those are the two constant solutions to this differential equation. And I encourage you to verify that. You know how to check a solution to a differential equation because we talked about that in chapter 1. Check both of those and make sure it works. But what we use these values for is to take the y-axis. So my y-axis in my coordinate plane is the vertical axis. This will look like a vertical line. And I'm going to plot these 2 points on there. 1, 3, like that. Okay? And now what I want to do is take a look at the 3 subintervals that this has created. So the 3 subintervals are this one down here this is negative infinity to 1. So negative infinity to 1. I'm creating like a little table out of this. And then this interval right here, 1 to 3. These are open intervals because at those endpoints, at 1 and 3 specifically, we know that those are critical numbers. Those give us zeros for our differential, for our slope function. And I want to determine where the slope function is positive or negative. 3 infinity is the last interval here. Now your book, I think, makes this table a little bit more involved. I'm going to make mine pretty simple. What I'm going to do is pick a sample point in the interval here and plug it in to my slope function. And I'll use the factored version of it. It's a little bit easier. So for example, within this interval, I know the number 0 exists. If I were to plug a 0 in to this function here, or this function here, either one, I get a positive 3 as a result. And the point is that it's positive. Okay, I get positive there. If I plug a number from this interval, say 2, into this function right here, or its factored version, 2 minus 3 is negative 1, 2 minus 1 is positive 1, negative 1 times positive 1 is a negative 1, or more importantly, it's just something that's negative. okay? And then if I plug a number from this interval into this function, or this one doesn't matter, let's say 20, it's a large number, both of these factors come out positive, and I know that positive times positive is a positive number. But what's the importance of this? Well, remember where this slope function occurred, right? This slope function, or y squared minus 4y plus 3, is here. And we're plugging numbers into this right-hand side to determine if it comes out positive or negative. Everywhere on this interval, no matter what number I plug in, this will come out positive. What does that tell me about my slope, though? Well, it tells me that my slope is positive, or in other words, my solution curve will be increasing on that interval. So that means that all along this interval right here, our function should be increasing. I use a little up arrow on my phase portrait to indicate that, okay? Using the same logic, on the interval from 1 to 3, we have negative slopes, indicating that our slope curve would be decreasing there. All right, and then in this interval from 3 to infinity, we have increasing behavior because our slopes are all positive there. So this is the first step of what we were asked to do. We were asked to create a phase portrait, and that's what this vertical line is. Okay, the table was a tool to help us fill that out. The next thing it says to do is to analyze the behavior of the solution curve passing through some point x naught, y naught. And what I'm going to do is take this phase portrait. This is oftentimes called a one-dimensional phase portrait because it's only on it only involves a single line. And I'm going to take that and think about it in the plane. So here's my coordinate axes here. I'm going to go like this, y and x, and our two equilibrium solutions were y equals 1 and y equals 3. Okay, remember those are equilibrium solutions, which means that they are constant solutions to our differential equation. What that means is that the as a solution to a differential equation, or a solution curve rather, we would see a horizontal line here because constant functions produce horizontal lines. I'm going to treat this as though I was creating a slope field, though. All the slopes would be horizontal or equal to 0 here. Same thing up here. Okay, so I use my equilibrium solutions to put these two horizontal dashed lines in the plane here. Okay, now let's suppose that we have some point x naught, y naught. And notice that by putting these horizontal lines in here, I've divided the plane into 3 separate regions. I'm going to call those regions R1, R2, and R3. And let's just pick some arbitrary point x naught, y naught in the first region. Okay? If I'm looking for a solution curve that's passing through this point, what does my phase portrait tell me about that solution curve? Well, according to my phase portrait, which is down here,